So in today's lecture, I want to talk about some of the issues of the code of the previous example, missing data example. And then I will talk about model selection, which is very specific to one of your homework problems. And then if time permits, then I'll go to chapter 8 today. So these are the three things we want to do. So in the last lecture, I suggested you to run the code, run this missing data code and see how it is working, how long it takes on your computer. And many of you have done it already, which is good. And now I'm receiving feedback from you guys. So one comment I received from a student who used some AI tool to make it more efficient. And the AI tool suggested to calculate some of the variance covariance matrices outside the loop. So if that is the suggestion, you can do that, but those variance covariance matrices, make sure they are not updated within the loop. So if they depends on the updated value within the loop, then you cannot calculate those inverse outside the loop. So let's look at this part. Sampling of the covariance matrix, okay? Sampling of the covariance matrix, this VEC1 depends on my data. This is that. And capital V, okay, so VEC1 depends on my data. My data is that data matrix which has missing value. So, and those missing values, missing entries are updated, right? So definitely we cannot do this calculation outside this major loop, outside this major loop. Okay, so VEC1 definitely not. Okay, let's move to this guy, capital V. Okay, capital V, cap V, depends on cap S0, which is the initial value, plus this guy, VEC1 multiplied with transpose of VEC1. So this VEC1 is updated every time, right? So we cannot do this calculation, cap V calculation outside the loop. That definitely is not possible. Okay, next is this one. This is what? This is inverse calculation. Inverse calculation of this Wishart matrix, right? And this Wishart matrix is sampled within the loop, and we calculate this inverse here. So this cannot be done outside the loop. It has to be here. Okay. So this is used in storing, and this is then used here, right here. So definitely this solve depends on this solve depends on ps.sm sigma. Okay, so what I'm doing here, this step is very unnecessary step. You see here, I can simply, because it's I'm doing inverse and again inverse calculation, right? So I would simply put out this one right here. Thank you for commenting on this code. Okay, so please Nothing wrong, but it is inefficient. I'm doing the same calculation again and again. So what you should do, you write n times this out, comma, comma, 1. Next is this calculation, cap PSI solve and solve capital lambda. Solve capital lambda was done outside the loop because that was initial value I gave, right? So that was done previously. But this one, this term 1, look at this term 1, depends on this out, which is sampled within the loop. So this cap PSI must be calculated here. And the mean theta depends on this cap SI. Solve capital lambda is already done outside the loop. And term 1 is right here. So please update this one. And then I'm storing. So change this line. That is the only thing I see. And then you give this code to some AI software and ask them to make it more efficient. Sometimes they give you good suggestions actually, but you cannot completely blindly rely on them. I have done several times. Many times it gave me very good suggestions, but still you need human touch to modify. Sometimes they do absurd changes. You should be careful about that. So this is one, but I think the major part is right here. This is very time consuming. This loop, J loop for J is very time consuming. Ask ChatGPT or something, some AI tool to make it more efficient. Because it has several if-else statements. If-else is generally very slow. A lot of inverse calculations are there also. But be careful and be mindful that some of the inverse you cannot calculate outside once because they depend on the updated value of the parameters within the loop. Okay, next is you guys have done already the missing data technique, right? So what are the comments? Go ahead.
Yeah, just that it created the imputed data, but then all I was able to do was calculate the mean of the new
So,
data set.
okay, that's a very, okay, so one of the students here in the class, he applied missing data technique, Miss Forest. So when you apply Miss Forest and want to run the Bayesian analysis, then you completely omit this part, right? This until this point, okay? So you omit all code starting from this. So essentially you omit the loop, J loop for J up to this point. You just run this part. And another thing is calculate this guy outside this loop, outside the loop of IT. Because you have already the imputed data. Imputed data is not changed within this loop of IT. And this line is simply calculating mean value, right, for every variable for that data set. So do this mean calculation outside this loop when you use missing forest technique. And then your code will be very simple. Analyze the data. But what is the issue? Issue is that you have theta posterior sample value and sigma matrix posterior sample value from one imputed data. So suppose you run it 5,000 times. and you do the imputation 10 times. In the end, you have 50,000 posterior samples. Combine them, combine all posterior samples for theta, and then calculate credible intervals for theta parameter. That will be analogous to what you are looking for, the confidence interval, right? If you just take only 5,000 samples for one imputed data and calculate the credible interval, that will ignore the uncertainty of imputation. But when you combine all the posterior samples from different imputations, that takes into account the uncertainty. Any other things? Did you try any other missing data techniques?
Yeah, I just didn't put them in the main loop, so I only did them one time.
Oh, you just generated the data?
Yeah,
you generated data.
Yeah, I was able to successfully fill in the missing values only one time, though.
Okay, that's good. And make sure you save your original data by something else and call it my data is as your imputed data, so that you don't have to change anything in the code, right? So in the next lecture, I'd like to see some concrete results, okay, in the next lecture. So what would happen if you calculate credible interval based on a single imputed data? It will be narrower than if you take into account multiple imputed data sets. And that should be evident in your numerical calculation. So you just consider one of the parameters, calculate the credible interval based on a single imputed data, and then do this based on 10 imputed data sets. See the difference. Now that difference may be very minute or could be large difference. It depends on the percentage of missing data. Your percentage of missing data is not that high, but when you have a high percentage of missing data, you'll see the difference. Appreciable difference. Another suggestion is that I will put a LaTeX file on Canvas, and you can compile that LaTeX file. It's very easy. You should have, there are several freely available software you can use to compile it. You just have to click compile that LaTeX file, it will compile and produce the PDF file. Another thing that we commonly use is the overlay. Overlay is freely available. And as long as you do not even need the premium subscription, that requires institutional subscription, because you are using it alone, you are not sharing with other people, and you do not have very large files. So which is freely available, use that subscription, you should be able to do it. So I put one LaTeX file just to practice for your practice. Do it, let me know how it goes. Then I'll replace all the PDF files by the LaTeX source file. All right, so this is about model selection. Questions? Yes.
Slide on the canvas yet?
This slide is not on Canvas. This slide. Okay, so let me do that. This is already. And I'll do it like this way. And my target is to eventually, maybe next year, convert everything to HTML file. HTML files are always accessible. And I'll use R Markdown to create that HTML output. So it is available now. All right, so this is the model selection question, and we might come back to this issue again, but this is very specific to one of the homework problems the other day student asked me. And this is your, I think, problem number 4.8. So suppose we observe, I'm just giving you example, 40 counts, y1, y2, y40, and these are the values. And we wish to assess whether these data arise from a Poisson distribution with fixed mean lambda equal to 2. I have added another question. If it is a Poisson distribution with an unknown mean lambda. So essentially two questions. One where I say Poisson distribution with lambda known, and I say it is coming from a Poisson family without specifying the lambda parameter. Verify if the data come from Poisson distribution. What we can do, we generate n observations, y1, y2, yn from Poisson lambda equal to 2, calculate the statistic. I'll talk about the statistic later. Some statistic T, repeat steps 1 through 3 m times. It should be 1 through 2 m times. M must be a large number, and calculate number of times this statistics is larger than the statistics calculated based on the observed data. If the above proportion is too small or too large, then the data do not come from the specified model. Okay. So what happens? If the data come from this model, then you would expect the statistic that you calculate from that distribution somewhere close to what you calculate based on the observed data, because observed data is a random sample of that same population. But if the statistics calculated from the observed data is too extreme compared to what you calculate based on the samples from the same population, then you suspect that the observed data is not possibly coming from the same population. That is why I say if this proportion is too small or too large, then you suspect that the data, observed data, are not coming from this Poisson distribution. Yes.
Thing with how T is distributed, based on your underlying distribution, would you have to worry about like very skewed distribution? It's like the expectation of T like isn't very close to the median.
This is okay. So this is the question. What if the distribution of the statistics is very skewed, right? I'm not looking at the distribution of the statistics alone. I'm comparing the distribution of the statistics with respect to its own sample. In the sense, suppose observations are coming, if the observed data are coming from the same population, then what is the likelihood that if I draw another sample from the same population and calculate the statistics, that newly calculated statistics will be somewhere close to the observed data. If it is very far from the observed data statistic, that means there is a discrepancy, right? And that discrepancy, what is the source of that discrepancy? Maybe the observed data is not coming from my assumed model. Irrespective of the distribution of the statistic. Irrespective of the distribution of the statistic. Yes.
What would we expect that proportion to be if it was perfectly matching Poisson distribution? Would it be 50%?
So that is the idea. So if the above proportion is too small or too large, then the data do not come from the specified model. Too small means like 0.01 or smaller than that, or too large, 0.99 or something, or 0.95. This you raised an excellent question. What should be the proportion? So if it is around 0.4 to 0.6 or 0.3 to 0.7, okay. But okay means what? Like this is very subjective, right? So there is a subjectivity in the end. Same thing when we compare with the p-value, right? So we say if something is smaller than 0.05 p-value, we reject the null hypothesis, right? So somewhere we put the threshold. That threshold is very subjective. Why 0.05? Why not 0.1? Or why not 0.001? Right? So the same subjectivity is there. I'll come to that part. But first, the concept. The concept is if this value is not extreme, that means there is a good agreement with what we observe. What is our assumption, model assumption is what our model assumption. Okay, choice of T. Choice, okay, so another thing, choice of T. This choice of the statistics, it could be the average, it could be the standard deviation, it could be the proportion of zeros in the data because I'm talking about count data, or proportion of observations exceeding a value, 5 or 6. Why 5 or 6? Because in this example, I wanted to verify if something is coming from a Poisson distribution with mean 2. So 5 and 6 is on the right end or towards the tail, right tail of the distribution. Therefore, I chose 5 or 6. But this concept is applicable not necessarily for the Poisson distribution. It is applicable for any distribution if you want to verify. Another thing you raised the issue, if the distribution of the statistics is skewed, what if the distribution statistics? Even if the distribution of the statistics is skewed, if I take two observations, two values from the same skewed distribution, and take the difference, what is the distribution of the difference? Is it very skewed? No, it is not very skewed. It is symmetric. The distribution of the difference, even for two skewed observations, is very symmetric. Very symmetric. So that means they are around 0. And you can do a simple simulation to verify that. So suppose I have a distribution, let's say it is a histogram or gamma 10,000, 1 and 1. Okay, so suppose you have a very skewed distribution, gamma 1, 1. you take two observations from this distribution. So this is, okay, so you take two observations, R gamma. And consider the difference of the two. Right? What we are looking here, look, this is, I'm looking at the number proportion, right? Proportion of times your observed data, your simulated statistics is larger than observed statistics, observed data statistics. So essentially you are looking at the difference, right? You can write it difference of t based on new observation minus t based on original observation, right? So that difference greater than 0. That thing you are looking at. So if you calculate the difference between two observations, and then this is equal to this, you see, irrespective of the distribution of the original observations, the difference will be symmetric. That means most of the observations are around 0, right? If they come from the same distribution. But if they don't come from the same distribution, then there is a chance, high chance, that it will be on the extreme end, either on the top end or in the bottom end, if they don't come from the same distribution. And that is what I'm using as a verification tool to calculate this probability, whether this probability is very small or very large. If it is so, then I can say most likely, I cannot say for sure, right? But most likely the observed data are not coming from the Poisson distribution. So this, and choice of t, as I said, could be average, standard deviation, all those things. Now, this is kind of, we wanted to do in the Bayesian class, right? In the Bayesian class, I'm saying this is the technique. You verify it and check it, whether it's a very small or very large. But in the classical test of hypothesis, they will calculate the p-value immediately. They will not consider different statistics. They will apply chi-square goodness of fit test. But I'll talk about that little later. First, take this data set, my data, and what I did, I calculated different statistics, mean, and then number of times you have zeros or the proportion of zeros in your data, standard deviation, or the proportion of times it is larger than 6. And calculated that quantity and came out to be these numbers. So the first number, 0.1160, is mean. I calculated mean of the Poisson data sampled from Poisson distribution with mean 2 and calculated what proportion of time it exceeds the observed mean of this data set. So it is about 11% of time. What proportion of time standard deviation exceeded the observed standard deviation? 81% of the time. What proportion of time? So this is not the standard deviation. The second one was proportion of time we observed zeros. And then this is for the standard deviation. And the fourth one is proportion of times is exceeded 6. So these numbers, some of them are small, some of them are large. but they are not that extreme small, right? Extreme small, I say extreme small is lower than 10%. Extreme high, I consider larger than 90%. This is a subjective choice, right? So based on that, we cannot find, that is why I say find strong evidence against the assumption the data follow Poisson two distribution. I'm not saying that data are coming from two, but we don't have very strong evidence against the Poisson distribution, not strong evidence. And so what do you do then? Then you say, we don't have a strong evidence. Strong evidence. Now in statistics world, we don't say, does not, you don't have strong evidence does not mean you have to accept the fact data are coming from Poisson two. That is why some scientists don't like statisticians, because they don't give the correct answer, straightforward answer. Maybe, likely, ambiguity, okay? Statisticians are not liked by scientists. That is the reason. Because we talk about the probability, right? So when you talk about probability, and the probability not always very close to 0 or very close to 1, there is an uncertainty. So we have to take into account that aspect. And you know, for generating this data set, I know the truth. What I did, I intentionally generated data from a mixture of distribution. And that mixture was, it was 30, it was about, this is 0.3, no, not 0.3, 30 over 40. Okay, so 70, okay. So it was 75%. 75% data came from a Poisson distribution with mean 2, and 25% data came from Poisson distribution with mean 3. So although it was a mixture distribution, but they are very close to each other, very close to each other. And we don't have a strong evidence that it is different from Poisson two distribution. You have to keep in mind your sample size is small. Sample size, I mean, small means 40 is not that large. If you increase the sample size, then definitely you will see these probabilities that we calculated will be much closer to 0 or much closer to 1 in that case. So when you make inference about something, not only these probabilities matter, but also the sample size matters. Now let us look at what we can do for the classical method. Classical method, everybody knows, but still, for the sake of completeness, I put it here. So the null hypothesis here is that data are coming from Poisson two, and the alternative is data are not coming from Poisson two. Step one, what do? You tabulate observed counts. Tabulate means you look at the distinct values of the data and record how many times each value appeared in the data set. So this is your data. And you can see minimum value is 0. You count how many times minimum value appeared. For example, 0 appeared 3 times. 1, 2, 3. Then next one is 1. So 3, 7, these are the counts, and you get it using any software. Then you calculate the expected counts under the model, under the Poisson two model. So in order to calculate expected count, first we calculate probability that x, the random variable equal to little x under the Poisson two distribution, and these are the probabilities you can calculate. And expected count, how do you do that? You multiply this probability by the sample size. Sample size n is 40, and you get these numbers. And combine categories if needed to ensure expected counts are all greater than equal to 5. You see here, I did it already because we had maximum value of 5 and 4. So 4, 5 were there, but they had very low frequency. So I combined them. So after combination, the expected counts for every group is more than 5. And then formulate the test statistics. And the test statistics formula is observed count minus expected count square divided by expected count and sum over all those differences. So essentially for the first group, it will be 5.40 minus 3 square divided by 5.40. Then for the next cell, it will be 7 minus 10.84 square over 10.84. So on and so forth up to the very last cell. So you take that difference and sum. It came out to be 5.44. This is the test statistics. And under the null hypothesis, the test statistics follows a chi-square distribution with degrees of freedom, number of cells minus 1. So how many cells we have? We have 1, 2, 3, 4, 5. 5 cells. So 5 minus 1, 4 degrees of freedom. So it follows a chi-square distribution with 4 degrees of freedom. And you check 5.44, that statistic value. If it is large, with respect to that reference distribution. Reference distribution is the chi-square distribution. If it is large, then the probability that the random variable, chi-square random variable exceeds that value 5.44 will be very small. So here it came out to be 0.245. It is not very small. Therefore, we fail to reject the null hypothesis. So the step is, if the p-value is smaller than alpha, what is alpha? Usually we test the hypothesis at alpha equal to 0.05 or 0.01. So if this probability is smaller than 0.05 or 0.01, you reject the null hypothesis. Reject the null hypothesis means you conclude data did not come from the Poisson 2 distribution. You can so here I did the hand calculation, but if you want, you can do this calculation by using this code, chi-square test. You put the counts, frequencies, and the probabilities, and rescale equal to true. Rescale, why do I do that? Because due to numerical approximations, these probabilities may not add up to 1, because I just put the 3 decimal places. And if you don't write rescale equal to true, then it will give you an error message. So that is why I gave that statement. So the chi-square statistics came out to be 5.44. It gave you the p-value 0.2447. Here the degrees of freedom is 4, which is the number of beans minus 1. Okay, and so we fail to reject the null hypothesis. We don't have very strong evidence against the null hypothesis. Okay, next thing is, what if I test if the data are coming from a Poisson distribution? So the null hypothesis here is data are coming from a Poisson distribution. You see here, I say a Poisson distribution without specifying the lambda. In your homework, you don't need to do that, but I'm just giving you the recipe for handling other cases. I tabulate the values same way as I did, and this time I don't know the value of lambda, but I estimate the lambda assuming data are coming from a Poisson distribution. So the MLE is the sample average, which is 2.25. So 2.25 is the average of these numbers. Okay, and that is the MLE. Under that MLE, I calculate the probability for every category. It is 0.1. It is 0.105, 0.237, so on and so forth. You see, these numbers are different from the Poisson 2 probabilities. And expected counts are calculated by multiplying n. N is 40 times these probabilities. Now this one came out to be 4.21, 9.84, so on and so forth. But this is a problematic number because it is smaller than 5, and it will give you an warning, okay, warning message, because chi-square test is valid if the expected count are all greater than 5. That is needed. So the right thing I should have done is to combine these two groups, okay, 0 and 1. I'm supposed to combine that. Then you do not need to worry about that warning message. All right, so if you, in this case, the chi-square test statistics, if you use this chi-square test, it gives you the test statistics value 4.063, degrees of freedom 4, and the p-value is this. But be careful, the degrees of freedom and the p-value both are incorrect here. So if you, in this case, both are incorrect because your degrees of freedom must be number of, it should be number of beans, I will correct it, number of beans -1 minus the number of parameters estimated. So it should be 3, not 4. Consequently, the p-value is 1 minus 4.064, 3, which is 0.2546. So this, do not take this p-value, do not take these degrees of freedom. And why? Because you have estimated the parameter, estimated the lambda parameter here. And the software does not know that it has been estimated. So what is your conclusion? So in both cases, your p-value is small, not smaller than reasonable level, 5% level. So you fail to reject the null hypothesis. You do not have a strong evidence against the null hypothesis. Now let's move to the Bayesian part. How to carry out this test in the Bayesian context. This is not for your homework, but this is the general guidance of Bayesian hypothesis test. So suppose in the Bayesian context, what you need? You need the data likelihood and you need prior, posterior. So we assume that yi given lambda follows the Poisson distribution and observation size is equal to 1 to n, let s equal to sum of yi, then the likelihood is this guy, e to the power minus n lambda, lambda to the power s over this. Assume a conjugate prior that lambda follows the gamma distribution with parameter a and b. Then the posterior is this. It is a gamma, a plus s and b plus n. Now, posterior predictive checking is the main Bayesian tool for assessing model adequacy. So for each posterior draw, lambda s, will be sampling this representative value yi s from the Poisson distribution, I is equal to 1 to n. We then compare replicated data with the observed data using the discrepancy statistics Ty. And that Ty could be sample mean, could be sample variance, number of zeros, maximum observation, maximum of yi, or tail count, such as number of observations yi greater than 5 or greater than 6, whichever is reasonable. And then calculate posterior predictive p-value, which is probability that these statistics greater than equal to these statistics calculated based on observed data, and which can be approximated by a Monte Carlo simulation. A value near 0.5 suggests good fit. Values near 0 or 1 indicate lack of fit. Again, in the Bayesian world, we don't use p-value. So a little bit of subjectivity is there. You choose what is close to 0, what is close to 1. So the algorithm goes like this. You sample lambda from this gamma distribution. This is the posterior distribution. And then you sample these values in observations from the Poisson distribution with this lambda that you have sampled in step 1. Then calculate the statistic. Repeat steps 1 through 3 m times. M must be a large number, and calculate this proportion. It's very similar to that idea we used previously. Only thing is that this time we are sampling from the predictive distribution, and previously we sampled from the Poisson distribution with mean 2. So with this data set, okay, so what I did, I actually plotted the graph. This is the histogram of the original data, and the blue dots, blue lines are the probability plot for the Poisson distribution with mean 2. Just to show you the difference. But in this Bayesian calculation, this Bayesian test, what we are doing, we are checking whether the data are coming from a Poisson distribution, not the Poisson with lambda equal to 2. No, I'm not doing that. A Poisson distribution. So set the prior parameters as a equal to 1, b equal to 1, capital M, okay, uppercase M, I set it 10,000 observations. And so this is lambda sampled from its posterior distribution. So this is my S, which is the sum of data. Okay, then we sample Y values from a Poisson distribution with this lambda, and sample size same as the data, original data sample size in. Calculate mean of newly sampled observations. I calculated number of observations that are equal to 0, standard deviation also. And so based on this, I calculated the proportion 0.4353 for the mean, okay? So that is very close to 0.5. So there is not much of discrepancy. But what if I look at the proportion of zeros in the predictive distribution, posterior predictive distribution, and compare it with the number of zeros in the observed data? That is 1. That is 1. And for standard deviation, it is 0.9135. So considering this scenario, considering this Bayesian scenario, what do you see? It's a strong evidence, right, against the null hypothesis. Null hypothesis is that data are coming from a Poisson distribution, but it's a strong evidence. Out of 3 statistics, 2 statistics are very extreme. Okay, so two of them are very extreme. So here you can say you can reject the null hypothesis. So, and say we have a strong evidence against the null hypothesis. So this is a wonderful example. I did not know when I simulated data or generated data that it will show such a wonderful difference between the classical method and the Bayesian method. Classical method and the Bayesian method.